Good day to everyone. My name is Li Chuan, or you can call me Li. And this is my colleague, Chan. And today, we would like to present to you the topic GDI phone fuzzing in kernel, Windows kernel for fun.
And these are the agenda that we would like to present for today's presentation. Basically, we would like to discuss two vulnerabilities, which are TTF font and .font file. And both vulnerability we will start with a short discussion, and then we will discuss how we're going to fuzz the vulnerability, and finally a little exploitation will be done for both vulnerability. And first of all, let's have a short introduction regarding the availability font within Microsoft Windows. Two group of fonts category, which are GDI and device, are among the fonts which exist in Windows. And GDI fonts consist of three types, which are raster, vector, and lastly is true type or open type fonts. Raster font is used to draw a single characters, whereas vector define the line segments and draw a characters in the font. Last but not least, true type or open type is a collection of line, curve commands, and also hints.
But today we will just cover the TTF font file and Microsoft bitmap font. Before we are talking about the vulnerability, here is a short introduction of TTF font file. Basically, TTF font file contain data in tables format that compromise an outline font, and the Windows scale this font to any size using the hint inside the TTF font file. And as a summary, there are three tables are involved in embedded bitmap in TTF font file. The first is embedded bitmap data tables, or short form is EBDT. And second is embedded bitmap location tables. And the last one is embedded bitmap scaling tables. And sometimes we also call the true type instruction embedded bitmap as a scalar bitmap or SBIT. And a stride is referred to a set of bitmap for a face at a given size. And this slide shows to you the example of TTF font structure.
And the EBDT table is designed to store the glyph bitmap data. And it begins with a table version number, and the rest of the table is a collection of bitmap data. And as you can see from the slides, the EBDT table is begin with the version header with version number, which is equal to 2000, and will followed by a strides of bitmap data in array. And you can see total of 12 strides are designed under this bitmap data table. The EPLC table identifies the size and glyph range of the SBIT and give the offset in index subtable. Same as EBDT, it begins with table version header, then followed by bitmap size table in array. And here is the screenshot of EBLC table structures. And next is EPSC table. It allows a font to define a bitmap strides. With no different with previous table, a version is defined, but the number of strides will also added at the header as well. It's followed by bitmap scale table, and each stride is defined by one bitmap scale table. This is the example of the EPSC table structure.
And now is another important information regarding glyph data. And this table contains the information that describe the glyph in the font file. But the most important is the glyph data tables is provide instruction for each of the following tasks. For instance, push data onto the interpreter stack. Second is managing the storage area, managing the control value tables, or even modifying graphic state setting, and so on. And every true type instruction is unique and specified by opcode value. For instance, hexadecimal number 0xb0 is representing ITRP underscore push B1 instruction, true type instruction, and B1 is stand for 1 byte. As you can see, this slide is the rest of the true type instruction. This is managing the flow of control, such as ITRP underscore jump and ITRP underscore LSW, and so on. And the second is managing the stack, managing the storage area. And here is the instruction for control value tables, managing the graphic state. And the last one is for the managing the arithmetic functions such as the add and subtract.
So now I believe you all have a basic idea regarding the true type font instructions. And those instructions will communicate or interact with FMT global graphics state type structures. And something interesting we would like to share with you all is this structure is an undocumented in MSDN or Microsoft library. Another interesting function is interpreter or ITRP underscore inner execute, where it designed to act as disassembler engine to process glyph data and map to correct true type instruction. And we also learned that some important parameters are constructed for FNT global graphics state type. For instance, the offset of 0 is represented as a state base, offset of 4 is represented to store the data, and it will continue until the rest until offset of 134. And please bear in mind of these parameters, which is CBT count, because all the exploit things will happen in this parameter.
And as you can see from the slide, here is a set of true type instruction in the font. The set of instruction is designed to provide a large number of commands to allow designer to specify how character feature should be rendered. And here you can see how ITRP underscore inner execute acting as disassembler engine to process the glyph data in the font file. Firstly, the ITRP underscore inner execute engine store the first opcode value from the font file, which is B0, into the ETX register. And the value of B0 act as index, and this engine, ITRP underscore inner execute, will locate the corresponding function. If you're interested to know all the full list of the instruction, you may refer to our article in section appendix 2. And this instance shows that ITRP underscore inner execute will map the opcode of B0 to the ITRP underscore push B1. And the following opcode value 00 is a parameter of the ITRP underscore push B1. The ITRP underscore push B1 instruction will push and store the 00 parameter into the state base of FNT underscore global graphics state type structure. And this structure will iterate over each instruction in an instruction set to define how character features should be rendered.
After having the short introduction, let's jump to the TTF fuzzer. And this fuzzer is created in the purpose of triggering TTF font vulnerability in different sizes. And some important functions are needed to ensure the fuzzer works. The first function is log font. And this object plays an important role in terms of determining the font attributes. And calling the create font indirect will returns to the hash font. However, this function are unable to work with the lower level font API. Thus, functions of get font data, get glyph index, ETX text out with ETO glyph index flag able to solve the problems. So if you are interested, you can refer to the URL at the bottom of the slide. They will provide more information regarding that.
And to sum up the overall process of the fuzzer, there are three important steps in the fuzzer. The first is the fuzzer will automating the installation of the crafted font in C Windows font folder. Secondly, the fuzzer will register a Windows class and creating a new Windows to display the font text in different size. And lastly, the fuzzer will remove or uninstall the font from the C Windows font folder.
And a range of font size in triggering the vulnerability is defined. As you can see, font size of range is increased from size of 0 until font size of 100. And you may change the value if you like. But please bear in mind that the log font fetch name must change according to the font you would like to trigger.
And there is a few physical font APIs provided by Microsoft to work with font at a lower level. In this TTF font fuzzer, we choose ext text out API function with the ETO underscore glyph underscore index flag to come out our TTF font fuzzer. And this is the screenshot of how is our TTF font fuzzer look like. And you would like to demo our fuzzer.
Okay, as you can see, two files are here in this folder. One is our fuzzer and one is the TTF font that we would like to trigger the vulnerability. And first of all, when we click the fuzzer, as you can see, the font size is increasing and displaying the font in various size. And this is how the fuzzers look like. First, we would like to, the targeted font is installed into the Windows system file. And then it will display the text file in Windows class, which is registered by the fuzzer. And if no vulnerability able to trigger, it will uninstall the font and install again with another font size. And this process will routine until the end of the process or any vulnerability able to trigger. And the fuzzer is created for the purpose of triggering, but not on attack work. Here we are going to explain the detail of attack work. The basic idea of this vulnerability is due to the required byte size of font after scaling is much bigger than its allocation. Thus, override to the next function could happen. To calculate the required byte after scaling, few values are required in order to do the calculation. These are the values we require from the EPLC, EPSC, and EPDT table. Okay. And as you can see from the slides, both PPEMS and PPEMY from EPSC table are created to compare with the size of font after scaling. Based on our fuzzing results, font size of 4 will cause the vulnerability to happen. Thus, the option of bitmap scale tables should always go to the bitmap scale tables 0, as both PPMS and PPMY are set to the 4. The value of substitute PPMS and substitute PPMY are described the size of stripes that exist as an S-bit in EPLC table. A total of 6 stripes are exist in the bitmap size table under EPLC with different values of PPMS and PPMY. However, the bitmap size table, the last bitmap size table, which is the bitmap size table number 5, is selected, and the selection is due to the value of substitute PPMS and substitute PPMY, where both values are equal to the value of PPMS and PPMY in EPLC. And also the crafted TTF font was originally designed as a monochrome. Thus, it always must have a bit depth value equal to 1. And now we have the value of image format and additional offset to index subtable, and both values are equal to 8 and 1C respectively. Table in this slide show the summary of the required data in order to do the calculation. So the following next few slides will show you the formula to calculate the required byte of font after scaling, which we learned this through reverse engineering. So we are not going to go through all the calculation, but we will go to the last one, which is the most important. And as you can see, the allocation byte of scaling bitmap data, which is original, is after we do the calculation is equal to 200. However, with the special crafter of TTF font, with the Y offset equal to 52, and we will, after do the calculation, what we get is the required byte of scaling bitmap data offset is equal to A40, which is much bigger than the it should be, the original it should be. So thus it can override to the next function.
And according to the calculation shown in previous slide, the required byte of scaling bitmap data offset is much bigger than byte of scaling bitmap data, and this condition will cause the integer overflow issue. The oversize of required byte of scaling bitmap data offset will lead to the improper memory access in subsequent function, and thus these circumstances will disturbing the function to perform normal. And the override issue happen at CVT count in structure of FNT underscore global graphic state type. The original value of CVT count should be 1, but due to the override incident happen, it changed to 81. And this will misuse the function to call others offset address within TTF font file data, where an exploit shellcode could place at this offset address. And to summing up the process of exploitation, first, inside the ITRP underscore RCVT instruction, the value, you can see that the value of CVT count control the flow of the execution. When the value CVT count equal to 81, and this will cause the flow of the execution call the another function, which is ITRP underscore get CVT entry fast instruction. And this function, which is ITRP underscore get CVT entry fast instruction, you may see that the highlighted instruction retrieve the contents of control value tables. And this slide show to you that the changing of CVT count will cause the ITRP underscore get CVT entry fast point to the TTF font data offset address. And this slide is you can refer to the WinDebug dumping result from the bottom of the slide. It shows to us the contents of the offset address FE29932C is exactly same as TTF font data. Thus, we can conclude that the shellcode can be manually put at this address. You can use any hexa editor to change the contents of the TTF font file. And the next true type instruction, which is ITRP underscore LSW, will perfectly call the address where the cell code can be placed to begin the exploitation. And now I would like to demo regarding this vulnerability. And before the demonstration, a few things I need to highlight. First is, this is Windows 7 operating system installed in VMware software. And now I log in as a guest ID. And this operating system actually is enable data execution protection, ASLR, and UAC, user access control as well. But this attack, the kernel attack, you no need to worry about the DEP, the ASLR, these kind of things. It's very straightforward, especially for the win32k.sys file. You can direct attack this kernel sys file, direct attack from the user mode. So this is our fuzzer, and this is the dexter.ttf file. So this is the text and dexter.ttf file we're using by the our font fuzzer and install into the C Windows font folder and doing the fuzzing. But I already set the font size is equal to 4 because from the previous discussion we already highlighted the font size. If font size equal to 4 will trigger the vulnerability. And second thing is, these tools is provided by the Microsoft. You can use these tools to load the dexter.ttf file to read the structure. And please bear in mind is, and this dexter.ttf file is actually is the same file we are using in Windows 7. So start from the address 15C. And another thing I want to highlight is, this is a Windows 7 kernel shellcode, and this shellcode actually is just a POC, just to prove that the shellcode is working. And end of the shellcode is a infinity looping, and this shellcode actually reach out the ring tree execution. Another thing is, this shellcode actually I grabbed from the one of my friend, and I take out the ring tree shellcode. But anyhow, you can copy from internet and then you can code by your own. And I crafted this dexter.ttf file and put the shellcode start from 15C inside the dexter.ttf file. And this file we are using to attack the Windows 7. Okay, now we are ready to doing the testing. And this is a WinDBG. And this WinDBG is a debugger. So currently we are connected to the Windows 7 kernel. So you may run any WinDBG command to fully control, because now you are already in the kernel mode debugging. So you can run any command to check the driver, to check anything. Break into the debugging section. But based on our analysis, we know that the BSOD actually happened in CSRSS.exe file. So the first thing is, we need to make sure the address of the CSRSS process. So from the result, we know that there is a 2 CSRSS.exe process is running in Windows 7 kernel. So you can choose either of the address. and change to the process context using the command .process/i/p and the address. And now we need to switch to the process context, and we need to confirm whether we are landed at process context. Yep, we already successfully landed at the process context csrss.exe file. And now the first thing we need to refresh our symbol before we launch the attack. So you may see the WinDBG starting to reloading the kernel symbol and user symbol as well. And from the previous slide, we already highlight that the function, the integer overflow function is happen at sfac underscore get s bitmap function. So now I set the breakpoint at this function. And don't worry and just ignore all the error message generated by WinDBG, as long as there is no error message regarding win32k.sys file. It may take some time to set the breakpoint. And yes. So you can use the command breaklist to check whether now, okay, we already success to set the breakpoint, and you just press go. So now we are ready to test our fuzzer. And what we need to do now is just double click on the phone fuzzer, and you may see now the fuzzer starting to loading the dexter.ttf file, but it hit the breakpoint we set in this function. And from the console of the fuzzer display, currently the fuzzer is using the dexter.ttf file, and the font size is equal to 4. And from the previous discussion, we already mentioned that the shellcode is calling in function itrp underscore lsw. So now I set the breakpoint at this function, and just press go. You may ignore all the instructions until you landed at this instruction. Move the contents of the ESI plus the offset address 0AC into the EAX. Let us see what would happen if we execute this instruction. And the DB-EAX is trying to dumping the contents of the EAX. Now you may see that the address inside the EAX, which is FE4E3T7C, the content 60 is equal to 60, 55, 8B, blah blah blah. Actually, exactly is our shellcode. Exactly is the same. So what this means is, you may craft the text.ttf file, start from this address. You can put your kernel shellcode, because now currently we are attacking the Windows 7 kernel. And the worst is, second instruction of the itrp underscore lsw is perfectly call our shellcode. So you can go inside the shellcode, and it's running perfectly. And we just press go. and you may see something is executed. This is just now I will highlight. This kernel cell code is just to do the infinity looping without any ring tree cell code. But anyhow, if you want to code your own cell code, you may refer to the internet. You can grab any kernel cell code plus ring tree execution, and you can craft it and put into this dexter.ttf file. This is provided in the I'll resubmit to the Brad Hack. You can download from internet. And before we start continue our talk, I would like to take some time to reboot the VMware server. And to make sure the thing is
in fresh environment, so we decided to revert back to the original state. The purpose is we need to make sure that the next vulnerability we would like to do is won't affect by this the first vulnerability. Okay, so it might take some time. So to ensure that it is really original fresh, so we decided to restart the Windows and also reconnect to the kernel WinDebug. So we are connecting to WinDebug now with debugging mode, and wait to start our Windows.
yep, done.
Okay. So while waiting the computer to start into the Windows, we may continue for our second vulnerability. So this is the second vulnerability we would like to present, and this is related to .font file, which is Microsoft Windows bitmap font. And let's come to some introduction first. The Microsoft font file come in two different types. First is new executable NE, then the second one is portable executable PE. And the .font files consist of two files, which are mkwinfont and fuzzer.py. Both are in Python file, and we will admit that these two files is not originally written by us. However, minor modification have been done upon these two small utilities file. And the fuzzer.py originally is generated only binary string of 0 and 1 only. So it might cause a lot of confusion with when we capture the some changing. So with the purpose of avoid any confusions and also convenience while capturing and monitoring the changes, string of A has been replaced instead of 0 and 1. And thus the function of string artoy has been modified by changing the given base of 2 to 16 as shown in the slides. And this is how the fuzzer look like. And the basic concept is like the first fuzzer with the different font size is called, and explorer function will call to display the function with the purpose of testing and triggering the vulnerability. So we like to have some demonstration regarding our TTF font. Yes, just now our Windows is already boot. So this is our fuzzer. As you can see from the screen, two font files consist in this fuzzer, which is the fuzzer and mkwin font. The fuzzer file first will call the generate the fd text.fd file. fd represents as font descriptor. Okay, so after that, the fuzzer will call mkwin font to convert the fd file to become .font file. And after convert the .font file, it will display the text in different sizes with different height and width size, and triggering the vulnerability, as you can see here. So you may see that different height and width size are displaying the font size. So the process will continue. If no vulnerability found, a task queue process will able to kill the font view process, and the process will repeat again with another font size, and this process will continue until the end of the fuzzing process.
Actually, this bug is regarding the MS11-077, and it is the kernel pool override vulnerability in Windows driver win32k.sys file. And this is a very interesting vulnerability, but based on the result of our analysis, it is very difficult to bypass the safe unlinking, which is just implemented by Microsoft in Windows 7 kernel pool. By the way, we also discover another BSOD, blue screen of death, which is the error message is driver overrun stack buffer during the testing. And for the first test, we define the font width equal to 498, as shown in the slide, within BMFD open font context function. The width value multiplied by 5, and the total size will be used to create a block of memory with n allocate memory API function. And the n allocate memory function allocate a block of memory size 160 bytes and insert a BMFD pull tag before the allocation. And this slide shows to you the font data will be processed within the vstretch glyph bitmap function. The font data AA will be used as index to read the contents from the following array, and there is total of 5 arrays will be used, which are, the first is AW stress 5W1, and the second BFA10171, and so on.
And based on the results of error message generated by WinDBG, and the vulnerability is due to the contents of pool BMFD override to the next kernel pool header. The analysis can conclude that total of 3 bytes of next pool header has been override. And this unlikely exploitation is due to the fixed value controlled by the Microsoft, and the routine in this slide is designed to grab the font data and begin the override to the next kernel pool functions. The index could be controlled, but not the value from those complexity calculations.
And this slide shows to you the result of the BSOD of bad underscore pool underscore header error message. And during the testing, another interesting BSOD could be happen with font width value equal to 681. And here is the blue screen result, and possible to bypass kernel canary in kernel land, but we gave out without any detailed testing because the patches already solved by the Microsoft. And we would like to show to you some demonstration regarding this vulnerability. And now I log in as a guest user ID, and same as previous testing, the WinDBG is connected to the Windows 7 kernel through the kernel mode debugging. So every error message generated by Windows 7 kernel will be intercepted by WinDBG. So from that we can analyze what is its cause, what is the root cause of this error message. So inside this folder there is 2 zip files. The first zip file is generated by our font fuzzer, and the width value is equal to 498, and the second is the width value equal to 681. So now I try to extract this zip file. And you may see this, why I keep saying this vulnerability is very interesting, because you no need to double click and open the font file. You just mouse over and highlight it to this font file. You immediately can cause your Windows kernel panic. And you may see the error message is generated by the Windows 7 kernel, and now is intercepted by WinDBG. And see what we can get. And if you're very expert in kernel debugging or any exploitation development, you should know about this command. And now we'll execute this command to check. So here you may see the error message actually happened in the csrss.exe process, and the error message is explained to us there is a override issue in the next kernel pool. So to prepare the second testing, I think I need some time to reboot my VMware server and revert back to the original state. And I think I don't need to reattach again the WinDBG. I direct to open the login as a guest user ID. And now we are testing the second value, which is generated by our phone fuzzer, and the which value is equal to 681. And you just highlight, then you may see your kernel is panic and the blue screen. Because now you will see the blue screen because I not reattach again using WinDBG. And another thing I want to highlight is this exploit actually, if you extract as a folder, if you put in the sharing folder, if somebody just trying to click that folder, it will also cause a blue screen. So maybe you want to play around some fun with your friend, you can test it. If your friend not go and patch not go and apply these patches. And thank you. I think that's all for today's presentation. And any question?
So, what privileges does a user have in order to install a font?
Sorry?
To install a font,
To install the font.
do you have to write it to Windows/fonts?
You no need to worry about the step how to install the font, because the fuzzer, our fuzzer will help you to do that.
Yeah, but what user do you have to run the fuzzer as? Do you have to be administrator?
No need.
No need.
So, an ordinary user can install the crafted font and run their shell code in the kernel.
I believe they were
Yes.
utilizing the guest account on the system, which is
If you want to install the phone, because as I know the TTF phone is it was related to the copyright issue. But if you want to download the new phone, you want to install, you just copy, you just right click and copy into the C Windows phone folder. But the fuzzer our fuzzer will help you to do that. And this is another interesting point we just discovered after we come out our fuzzer, because just now I will show to you all that I log in as a guest ID, and if you're doing copying the things into the C Windows folder, right, you'll pop out some message, something like UAC asks you to key in the administrator ID and password. But just now, when the fuzzer is executing, you can't see anything is pop up, right? So what we suspect is the C Windows font folder is not protected by UAC. So you just need two files. The first is the crafted font, the Dexter.ttf, which is we already provided to the Red Hat, and our fuzzer. You just put together in the same folder, and you need, by anyhow, you need to install some plugin like PyWin, and you can play around with your Windows 7 kernel. Any question?
Pretty cool.
Thank you.
Thank you.